That took a while to start up. Answers to quiz number 1. Airplane turns a complete horizontal circle in 2 minutes. Nice try, Mr. Dueck. Nice try. 120 seconds. You're not going to get me to put a 2 in for time. Plane speed is 170 meters per second. What's the radius of the circle? Well, they gave me speed. They gave me radius. This equation is not on your formula sheet. Sorry. And it's the equation for centripetal or circular speed, which is distance over time. Not on your formula sheet. Oh, I'm pretty sure that means that the radius is going to be the speed times the period divided by 2 pi. Is that right? Times by t. Yep. It's going to be 170 times 120 divided by 2 pi. For this to occur, we need to have a radius of 170 times 120 divided by bracket 2 pi. You get a radius of 3,246.3.25 times 10 to the third. About 3¼ kilometers. I think I yoinked these numbers from, I think I was Googling fighter plane stats or something like that. So this would be a fighter plane doing a fast, fairly, because 170 meters per second, it's about 300 or 400 miles an hour. So you're going fairly quick. What's the centripetal acceleration of the plane? I think I'll use v squared over r. Although you could use 4 pi squared r over t squared. No matter what, I have to use r from part A. So it's going to be 3246.8 squared. No, that's the A, Mr. Dueck. How about putting the speed there, Mr. Dueck? Duh. 170, whoops, sorry guys, squared, divided by 3246.8. 170 squared divided by that there number, and you get 8.9? Almost, but not quite 1G. 1G would be 9.8. So you'd feel it, but most of you could handle it and probably handle it for an extended period. For both of these, if you get the right answer, of course, 2 out of 2. Otherwise, I would give you 1 mark for that, half mark for that, half mark for the answer. I would give you a half mark for that, 1 mark for that, and a half mark for the answer. If you got A wrong, but you went 170 squared divided by whatever answer you got for A, and you did that correctly, you can get 2 out of 2 for B, even though you got the wrong answer. Did anybody use the period one? 4 pi squared r over t squared? Does that need to do that? Okay, good. Number 2, what centripetal force is needed? Okay. I think I'm going to use the 4 pi squared r over t squared version of acceleration. Now, they didn't give me the period. What they did give me is the frequency. If I know the frequency, what's the period? If I know one, I know the other one. 1 over 5 seconds, or 0.2 as a decimal seconds. So the centripetal force is going to be 12 4 pi squared, radius is 6, divided by 0.2, or 1/5 squared. 12 times 4 pi squared times 6 divided by 0.2 squared. Do you get a centripetal force of 71, that there? 71,000? 7.11 times 10 to the 4th. Now, at first I thought, holy smokes, that's really big, because it is really big. And then I went, hey, wait a minute. We're taking a 12-kilogram object, bowling ball, and on the end of a 6-meter chain, it's spinning around so fast that it's spinning around 5 times a second. If you were spinning around a bowling ball on a length of chain that was 6 meters long, 5 times a second, I think that would be a huge force. So I'm okay with that answer. At first, I was a little uncomfortable. Now I'm like, yeah, that makes sense. For 3 marks, okay. I'd probably go 1 mark for that. Oh, heck, 1 mark for the numbers, 1 mark for the answer. I don't know. They want the centripetal acceleration in number 3. And I think I'm just going to use v squared over. They don't want the force. I don't need to multiply by mass. They didn't give me a mass anyways. Is that a hand up, Elijah? Or just, no? Okay. Radius, careful. 0.25. The 2 ways they'll try and trick you with the radius is they'll give it to you in centimeters, or they'll give you a diameter. And you've got to divide by 2 to turn it to a radius. I won't do that intentionally, but it might show up in some of the exercises. Oh! I think I can do this in my head, because 5 squared is 25, divided by 0.25. Is the answer 100 even? Why is that wrong, technically? Sig figs, how many sig figs is that? 1. I've told you I want everything to 2 or 3 sig figs. Again, I'm not taking marks off this year, but back when there was a provincial exam, I would, because on the provincial they would, so I had to beat it out of you guys. Turn the page. Ferris wheels, cool. This is a job for a free body diagram. They want the force that the bench exerts. No, they don't. They want the normal force. And do you know why they want the normal force? Because the normal force is, look up, fun. Huh? Eh? Huh? Eh? Huh? Okay, fine. What are the forces acting on this person? Get the obvious one, mg. Now, we're at the top, so I know normal force must be smaller because I'm moving in a circle, and what I've tried to tell you is, you know, if you're moving in a circle, the net force is pointing towards the center. That gives you a lot of information about what the free body diagram has to look like. It's going to be mg minus Fn equals mac. It's going to be mg minus mac equals Fn. It's going to be mg minus m. Oh, they gave me the period. 4 pi squared r over t squared. It's going to be mass 65. 9.8 minus 65 times 4 pi squared. Hey, radius, 9 all over 45 squared. I didn't do a very good job of using my space here, did I? You know what, Mr. Dueck? Let's be clever. There, that's better. What do we get? Let's see. 65 times 9.8 minus 65 times 4 pi squared times 9 divided by 45 squared. Looks right. Do you get 625.6? 626? And I think looking at this, the person feels a little lighter because normally they feel mg, and this time they're feeling mg take away something. Not much lighter because 45 seconds for a Ferris wheel to go around, that's a painfully slow Ferris wheel. What's the force that the bench exerts on the person at the bottom? Well, at the bottom, mg down, but this time, normal force is winning. In fact, normal force is going to be m4 pi squared r over t squared plus mg. Hey, you ready? Normal force is going to be, plus. Same equation, basically. Do you get 648? Like I said, not much difference. This is a painfully slow Ferris wheel. Newtons. Do I need to do part marks, or are you guys okay? Okay, 2 out of 2. Hey, space station. We want to simulate gravity. It's artificial gravity. Space station has a radius of 160 meters. We want to simulate, what would the period be? Okay, so here's really what we're saying. We want to create a fake little g. And that's going to come from the circular acceleration. Now that's the shortcut. What we really said was this. We really said if you're moving in a circle, the normal force is what's pushing you in a circle. But then we said in this case, what do we want the normal force to be? We want the normal force to be 75% of mg. That's what we want. Conveniently, this will work for kids and grown-ups. They want the period, so I'm going to make sure I use the equation that has the period in it. And I guess if I get the period by itself, I think the t squared can move to the top at the same time as the 0.75 g can move to the bottom and square root. I think t is going to be the square root of 4 pi squared r all over 0.75 g. The period is going to be the square root of 4 pi squared. I tried making these numbers a little more realistic. 75% of 9.8. And you get 4 pi squared times 160 divided by 75% of 9.8 square root 29, come in, 29.3, is that right? 29.3 seconds. So give yourself a score, please. Orbits. Example 1 I wrote here. Draw a force diagram for this mass little m in orbit. By the way, it's traditional when we're analyzing this, we'll often use a capital big M for the planet and then a lowercase little m for the satellite or the spaceship or the moon or the asteroid or whatever it is that we're talking about, the orbiting body. So, see little m? What are the forces acting on it? Now, normally I'd say get the obvious one, and I am sort of gonna say that, but we have to be careful. What path is this little satellite tracing out? A circle. So where must the net force be pointing? Ashley, what's that mean with the towards the? Yeah, okay. So I know there has to be. What force is that? Don't put FC, that never shows up on the free body. What's pulling the satellite in a circle? Okay. Although, don't be putting mg, because now we're cosmic, and as you move further and further out, the force of gravity changes. What we're really going to be using is that one. It turns out an orbit is circular motion with gravity as the inwards force. Now this bugs some people because, Mr. Dueck, if that was my free body diagram, shouldn't the satellites all be crashing into the Earth? Shouldn't they all be falling? Those are two different questions. The answer to the second question is, yes, they are all falling. The answer to the first question is, no, they're not crashing into the Earth. How can we do both? Well, let's see. Example 2. A 10,000 kilogram satellite is orbiting 20,000 kilometers above the Earth's surface. A says, write force equations. And then B says, find the orbital speed. I don't like my units, that 20,000 kilometers. I'm going to change that. So how do I go from kilometers to meters? Times by what? So I'm just going to quickly go 20,000 times another 1,000, and I get 2 times 10 to the 1, 2, 3, 4, 5, 6, 7. So I'm going to make a little note here. 2 times 10 to the 7th meters. Okay, now I'm a little happier. What do they want me to do in part A? Write the force equations. Well, this is sort of a job for a free body diagram, kind of. Oh, wait a minute, we've already said that. We've said that. What path is this satellite tracing out? A circle. Who's winning? Who's FG? Who's losing? Trick question. No one. I guess if I apply my circular motion, what we've done for the Ferris wheel and for the car going around the corner, I think, Neve, the force equation is going to be this. Gravity is what's creating the centripetal force. That's your force equation. Now, I can break this down a lot further. How can I write gravity? Don't say m little g. That's only on the surface of the Earth, and we're a long ways from the surface of the Earth. What's the universal equation for gravity? Big G, big M, little m, over r squared. What's the equation for centripetal force? Well, it's going to be mass times acceleration. Which acceleration? It depends. Read the question. Did they give me or are they asking me to find speed, or did they give me or are they asking me to find period? Speed. Oh, speed. So I'll use the one with the V in it. That's the equation that describes an orbit. Hey, Mr. Dueck. Yeah? I noticed something. What do you notice? Turns out, doesn't matter how heavy the satellite is. As long as you give it the right speed, it'll orbit in the right place. No problem. Well, Mr. Dueck, if the mass cancels, why don't we build cities up there? Keeping it up there, the mass cancels. Getting it up there, believe me, the mass does not cancel. Which is why, by the way, we built the ISS in sections, and we're still adding to it in sections. We send up little sections, and we're building it together like a giant Tinker toy, a giant Lego toy. But once it's up there, the fact that the ISS right now, it's almost the width of a football field. It's pretty big. It'll stay up there just fine. Because once it's there, M cancels. Little m, mass of the satellite. By the way, what's big M? Mass of what? Earth, if you're orbiting around the Earth. Sun, if you're a planet orbiting around the sun. Or whatever situation I give you. Okay. Double check. Do I know big M, the mass of the Earth? Yeah. What do they want me to find? V? You know what? Let's get the V by itself. Oh, I notice one more thing. This R right here could move to the top, and that would give me 1 R on top, 2 R's on the bottom. You know what? Actually, what happens is this. That R cancels one of those. How would I get the V? Because it says find the orbital speed. Oh, and by the way, Jordan, that orbital speed is this one here. It's the one tangent to the radius. That's what we're talking about. How would I get the V by itself? Square root, yeah. Looks like, Peter, orbital speed is the square root of big G, the universal gravitational constant, 6.67, mass of whatever planet you're on, divided by whatever your orbital radius is. Okay? Now we have to be a little bit careful, Alex, before we start to substitute in numbers, because of that word right there. This number right here is 2 times 10 to the 7th, but that is not the orbital radius. The orbital radius is that. How can I find the orbital radius? Well, how far from here to here? 2 times 10 to the 7th. How far from here to here? Wait a minute, I know that. Isn't that, yes, I saw Sammy go to her formula sheet. Isn't that the radius of the Earth? And that is on my formula sheet. You know what? I'll make a little note here. I think the radius of orbit is going to be the radius of the Earth plus the altitude, the ALT. It's going to be 6.38 times 10 to the 6th plus 2 times 10 to the 7th. So you're going to have to read carefully, Kelly. Sometimes they'll just give you the orbital radius, in which case, good, you don't need to add the radius of the planet. Sometimes they'll give you the altitude, in which case you better track down the radius of the planet and add that to it. Hey, what is the orbital radius? Can someone crunch that for me? Is it 2.638 times 10 to the 7th? Yeah? Now I'm good to go. I can now tell you that the speed with which this satellite needs to orbit the Earth, if it wants to orbit the Earth at an altitude of 20,000 kilometers at an orbital radius of 2.638 times 10 to the 7th, the speed you need to give it is 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 mass of the Earth divided by 2.638 times 10 to the 7th, hit equals square root. This is going to be orbiting the Earth at 3,888 meters per second. Any faster or any slower, it will not be in a stable orbit. Its orbit will either decay or it will start to move further and further from the Earth. Yep.
Do you theoretically get something orbiting the Earth 2 meters above its surface?
Good question.
If it was going past there?
Good question. Preview of coming attractions. We'll do one in a we'll actually calculate that in a couple examples. You know what? It's going to be 3.89 if I round off properly, isn't it? The short answer, yes. The closer you are, the faster you have to travel. And of course, on the Earth, you're going to have to deal with air resistance. In fact, we've crunched the numbers. You'd burn up with just from the friction, from the air friction. In fact, there's an old physics problem where you calculate how fast Santa Claus would need to actually travel, if he could, to visit every little boy and girl in the Western European, North American world in a 24-hour time span, and he would clearly burn up. So even if somehow the technology was there, you would need magic. You'd need magic physics. But here's what I want you to notice, which is kind of cool. Orbital speed is independent of the mass of the orbiting object. It depends only on the radius and the mass of the planet. Now, I'm going to write the equation here, but we're not going to memorize it. So the equation that we derived was this. Instead, memorize when you're in orbit, gravity is what's pulling you in a circle. If you start there, Jordan, you'll be able to derive, I think we're going to end up with 4 different equations. You'll be able to derive them all. You can memorize all the 4 different ones, and it depends. I can either give you the radius and say find the speed. I can give you the radius and say find the period. I can give you the period and say find the radius. I can give you the period and say find the speed. I can give you the speed and say find the radius. I can give you the speed and say find the period. You know, don't. Here's what I want you to realize. This here, free body diagram. Gravity is what's pulling you in a circle. You can do some neat stuff with orbits. Got some interest. We'll have more fun. So, I wrote down here, fill in the proof below to show that when an object is in orbit, its inwards acceleration is the same as the gravitational field at that distance. Say what? I'm telling you, the astronauts on the ISS have a gravitational field. Here on the Earth right now, you're all in a gravitational field of 9.8 newtons per kilogram. The astronauts are about 8.9-ish. We'll talk about why they're floating then, because they shouldn't be, should they? We'll talk about that. First of all, A equals, right? A equals V squared over R. And then I wrote underneath there, substitute orbit speed. Oh, that equation that we wrote in the box, which I said don't memorize it. But we said, oh, that was the square root of big G, big M over R. If I plug that into there, first of all, if I go V squared, I guess what's going to happen is the square root will just cancel. And I'll get big G, big M over R. Oh, but there's already an R down there from the V squared over R. What's a better way to write RR? Which I'm pretty sure last class I told you was the universal way to calculate the gravitational field anywhere. That means, I'm telling you, and you try and explain this to a non-physics person and they won't believe you, the astronauts on the ISS are experiencing gravity, but they're floating. But they're experiencing gravity, but they're floating. Well, here's the key. They are in free fall. And here again is one of the many, many reasons why we have so much respect for Sir Isaac Newton. Because in 1580, long before people understood what outer space was, he answered the question that Michael asked a few minutes ago. He said, imagine a big mountain with a very powerful cannon. A little thought experiment. Cannon because that was the technology of the day. He said, it seems to me that you could fire the cannon and it could land there. But if you put more gunpowder into it, a bigger velocity could land there. In fact, if you put more gunpowder in it, Neve, it could land right about there. He said, I'll bet you there's an amount of gunpowder, there's a specific velocity, so that even though it's always falling, it's falling towards the Earth but traveling sideways at exactly the same curvature of the Earth. So it's in free fall, but it's never going to hit the Earth. We have a word for that. Begins with letter O and rhymes with orbit. The astronauts are in free fall, but what we did is we gave them just the right tangent velocity so that they're free falling down and moving sideways, exactly matching the curvature of the Earth. That's why they experience no normal force. They're feeling exactly what I felt when I jumped out of an airplane. Imagine I jumped out of an airplane. They're feeling exactly what I felt, except I felt the wind on my face, so I was aware of falling. They're in an enclosed room. They don't feel the wind on their face. That's it. But the fact that they can maintain that no normal force for a long time, they'll call it microgravity to distinguish from no gravity. That means you can do some really neat experiments up there. You can do some very interesting science applications up there that you just can't do here on Earth. So, the fact that an object is in continuous free fall is interesting. Number one, it means that things in orbit are always falling towards the Earth, even though they never get there. Number two, it explains why astronauts seem to float. Both passengers and the ships are in free fall. They're falling at the same rate. And so that means the ship can't exert a normal force. And Curtis, you may have noticed one of my ongoing themes already from Physics 11 last year was what you guys think of as your weight is actually the normal force. That's why any good ride mucks around with that. The astronauts are all experiencing a normal force of 0. Oh, and it also means that the astronauts experience continuously, until they get used to it, it takes about 2 or 3 days, the physiological feeling of falling. You talk to any astronauts, Chris Hadfield talks about it, the first 2 days, you're throwing up like crazy. You just, no matter how good you think your stomach is, your brain is on overload. Everything has to readjust. Oh, and then Chris Hadfield, when you come back to Earth, he says, boy, you're trying, because they hustle you out of the space capsule, they put you in front of the cameras because the press is there, and he says, you just want to puke like crazy. And as soon as you're done that first interview, you're so weak anyways, they hustle you into an ambulance, and you're throwing up, and you're throwing up, and because now it feels like you're falling when you're not. That feeling is just always there. Put your pencils down. Answering Michael's question. In a cartoon, a character kicks the football the wrong way, but the football orbits the Earth and still goes through the uprights, but from the back end. What speed would the football have to be moving if this was the case? B, how long would it take the football to make this trip? And C, why can't this actually be possible? We've already answered C. What's the big problem with doing it? Air friction. In fact, that's why I wrote in brackets, if we do ever have a moon base, absolutely we would have satellites maybe 300 or 400. We would find the highest mountain on the moon, go maybe 100 meters higher than that, put all your satellites there, absolutely, because there's no friction, and you would see them. They'd be very, very handy. Heck, that'd be great. We could do that easily. We'd have to give it a lot of kinetic energy, but still, very doable. So what does A want us to find? What does A want us to find? What path is this football tracing out? A circle. What force is pulling it in a circle? So, gravity equals centripetal. Which gravity? Not mg. Wait a minute, we're on the surface of the Earth here, Mr. No, we're going to use the universal. Big G, big M, little m over r squared equals m. What am I being asked to find in part A? I better use the one that's got the speed in it. V squared over r. Mr. Dueck, you didn't tell me the mass of the football. Nope, I didn't. Oh. V squared. How to get rid of the squared? Now this is the equation that we wrote in the box a few minutes ago, but I wanted to show you why you don't need to memorize it. It's a 5-second derivation. V is the square root of big G, big M over R. So on the Earth, that's going to be the square root of 6.67 times 10 to the negative 11. Mass of the Earth, which is 5.98 times 10 to the 24th, all over radius of the Earth, which is 6.38 times 10 to the 6th. Square? Nope, the R canceled. Did I type this in right? Oh, thank you. I forgot to square root. Good gosh. The video said 8,000 meters. Is that 8 kilometers a second? Pretty close. They rounded off. Okay. 7.91 times 10 to the third. Okay. What does B want us to find? Period. What path are we tracing out? What force is pulling us in a circle? Gravity. So are you saying that anytime we're in orbit, I can go like this? You would be correct, sir. And gravity is always going to be big G, big M, little m over r squared equals m. What are they asking me to find this time, Nate? I better use the one that's got the period in it. 4 pi squared r over t squared. Mr. Dueck, you didn't tell me how much the football was. No, I didn't tell you the mass of the football. Did I? Now, pay attention here, please. The most common mistake that I see is kids want to cancel out an R. Where are the R's on the left-hand side, top or bottom? Where are the R's on the right-hand side, top or bottom? Stuff moves diagonally. Actually, that R is going to move down there, and I'm not going to end up with an R squared. You know what I'm going to end up with? An R cubed, or these R's would move to the top, but I'm going to end up in this equation with an R cubed somewhere. What are we trying to get by its side, Nate? By itself, Nate? You know what? Let's move the t squared to there, the r squared to there, and the big G, big M. Can we do that all in one big step? I think we'll get this. A 4, a pi squared, and r cubed over big G, big M. Except that's t squared. Help me out, Nate. Is that okay, folks? I hope. And now, I mean, it's plug and chug. It's complicated plug and chug. The numbers aren't convenient, but such is the universe. But it is plug and chug. It's going to be 4 pi squared, 6.38 times 10 to the 6th cubed. Better make sure you know where your cubed button is, or your to the power of your exponent button is on your calculator, divided by 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. Okay. Whew. I think I wanted to put that in brackets. 6.38, might not have needed the brackets, but just to be safe. Divided by bracket 6.67 negative 11 times 5.98 24th. That looks good. Square root. About 5,070 seconds. By the way, can you divide that by 60? How many minutes? What? Yeah, you'd be going around the planet every 84 minutes. The space shuttle, the ISS, sorry, not space shuttle, the ISS, it's every 92 minutes, I believe. Goes around the Earth every 92 minutes. How many of you have seen the ISS passing overhead? Really? Pause the video. Continuing on. Yep. Yeah, we got 8 minutes. So what can we do then? We can find period or radius or speed if we're given period or radius or speed. We just have to pick the correct circular motion equation. So, example 5. What does example 5 want us to find? What does example 5 want us to find? Got to be fussy. It actually wants the altitude. I'm going to find the orbital radius, then I'll subtract the radius of the Earth, and that should tell me how high above the Earth it is. Okay? Keyword here, all of you are going to underline this. Underline the word orbit. If you know you're in orbit, what path are you tracing out? A circle. What's pulling you in a circle? In other words, if you know that you're in orbit, you can almost always, this is almost the equivalent of it's of a force, do a free body diagram. If you know you're in orbit, you can say, oh, gravity equals circular. Gravity doesn't change. Centripetal force is going to depend. First of all, don't forget to write the mass, because it's mass times acceleration. Which acceleration? Yeah, which the one with the V or the one with the T in it? How do you know? Oh, they gave me a period. In minutes, I'll have to do an adjustment, but okay. So I'm going to use the 4 pi squared r over t squared. By the way, 300 minutes, how many seconds? 18,000? There's my period. Okay. Hey, they didn't need to tell me the mass of the satellite. Sometimes they will, but they don't need to. What did you say we're trying to find, Michael? Let's get the r by itself. I think I would move these two here to the top. I'll have an r cubed over here. The t squared can move to the top, and the 4 pi squared can move to the bottom. By the way, it was for this equation that I taught you that stuff moves diagonally. For this equation right here. Because I hope what you can see is we get this. Big G, big M, t squared over 4 pi squared. That equals r cubed. Is that okay, Kelly? Oh, hey, how do I get rid of a cubed? Holy smokes, you mean we actually use cube root in the real world? Yeah, cube root. By the way, this is your time for all of you to figure out where the cube root button is on your calculators. And I'll help you if you can't find it, but hopefully you can find it. So r is going to be the cube root of big G, big M, t squared over 4 pi squared. And again, don't memorize that. Know this, if you're in orbit, gravity equals centripetal. We can derive whatever we need to derive. There's 4 or 5 other versions of this I can come up with. It's going to be 6.67 times 10 to the negative 11. Mass of the Earth, 18,000 squared. What's the orbital radius? Change colors, Mr. Dueck. Yeah, lots of calculator typing. You got to get good. Nice shot. Do you get, this seems big. Did I type this in right? Oh, I square rooted. Dummkopf. Cube root, Mr. Dueck. You even wrote it wrong. Cube root, Mr. Dueck. Where's my cube root button? My cube root button is math cube root of that. Do you get that?
Yep.
That's better. 1.48 times 10 to the 1, 2, 3, 4, 5, 6, 7. Now that's its distance from the center of the Earth, which is not what this question wanted. To change this into an altitude, that's going to be the orbital radius minus Earth's radius. Right? If you think about it as a picture, there's the Earth. We just calculated this distance right here. To find that, we'll subtract radius of the Earth. So if I go this number, take away 6.38 times 10 to the 6th, orbital radius, or altitude is 8.47 times 10 to the 1, 2, 3, 4, 5, 8.47 times 10 to the 6th. Meters. Pause here. We'll pick up with this on Friday. Orbits. Very cool.